Then I'm going to share the screen. So I think we talked about the Higgs boson, its importance, and we know that particle physics is not complete. There will be other things discovered. The major international effort is at CERN, and they have at least 50 new possible discoveries in the works right now. And I put this one thing in here about how to detect neutrinos. So neutrinos have no charge. They have very little or negligible mass. And therefore, it's the hardest thing to detect that we know of. Although we do have things that are simply not even detected. So I talked a little bit about the IceCube telescope. And anyway, now we're beginning to learn how to detect neutrinos and how to figure out where they're coming from. Which really brings us to how would this be used? This would become a new way to look at the universe, neutrino astronomy. You know, we look at this up to the sky and we see the star, we see, you know, the sun, the moon, and all this kind of stuff, but that's only our visible range. Humans are so smart that they develop all kinds of ways to see the unseeable. When a human looks out and observes the world, we see almost nothing because what we see with our eyes are simply the visible spectrum. But we've created machines that help us see infrared and ultraviolet and gamma rays and now even neutrinos. Some of these machines, in order to detect these things, are some of the biggest machines that mankind has ever built. And there's practical uses, like muon tomography is one. We can look inside pyramids and look inside volcanoes. It's crazy what we're able to do. And all this stuff is really just in its infancy. As soon as you find a new way to see something, to observe something, then goes the process of discovering what we could not have seen without this technology. That's why I think astronomy is one of the most important things that mankind can do. Like I've said before about science, science doesn't belong to Americans, it doesn't belong to Chinese, it belongs to humanity. So here's some stuff about gravity that Einstein had predicted and became famous for. General relativity simply says that gravity does not simply pull matter through empty space. Instead, matter causes a curvature in space-time continuum that makes it look that way. And so, do we just say that, okay, we proved some of the stuff that Einstein said, so now is it just there as fact forever? No, they're constantly trying to find ways to revalidate or question anything that's known. So in 2018, there was a very important experiment where they again validated Einstein's concept of space-time. So here's another thing that we have that's brand new in order to detect and understand the universe: gravity waves. So gravity waves were first postulated in 1905. Einstein predicted it. They were indirectly proven many years later. And then in 1994, they built the first machine ever to try to actually measure gravity waves. So I don't have a picture of it, I probably should here. But what they do is they take two distant laser sources and they cross the lasers like this. So the lasers are such that there's no interference with them. But if the points where they originate from has any difference in distance between them, then that's going to show up as interference in the laser wave. And so they made one in 1994. There's a little bit of a description about it. And guess what? They didn't measure anything. They couldn't find anything. So did they give up? No, the humans don't give up. Many humans give up at the slightest little amount of effort required, but scientists are the ones that never give up. So they made another one, and let's see, in 2015, they actually first measured the first gravity wave. So it changed the distance between these mirrors that reflected the lasers. Look at the size of that. It's about 1/1,000,000th the size of an atom. So why is that even possible? Because a light particle, theorized and also known as a photon, is so much smaller than an atom. An atom looks huge compared to it. So that's why this is possible. So anyway, they've discovered several more. And then in 2017, they detected a small gravitational wave was detected and associated with the merger of two small black holes. And they're developing a new technique. I don't really understand it, but they're going to say that this is going to increase the sensitivity by 4-fold. So here's a brand new way to look at the universe. And then I just wanted to give you a large summary about the Big Bang Theory and all this kind of stuff. Something that you can go on to kind of add things to as things become discovered. So before the Big Bang, there was only energy. The four forces of the universe were combined. The temperature was just not even conceivable. So the Big Bang happened something like 14 billion years ago. In a fraction of a second, the universe expanded and the temperature cooled enough for matter to form. So where do they get this concept from? If you take a gas and you compress the gas gets hot. If you take a gas and let the gas expand, the gas gets colder. So this is something that's been known for hundreds of years. So what they're doing is simply applying that to the universe. So here's the speculated time zone in about, 400,000 years after the Big Bang. Hydrogen and helium were able to capture electrons and the first stable atoms were formed. And photons, which are particles of light, no longer had enough energy to ionize every atom. So that means they're able to pass through the atoms without being absorbed, making light and making the universe now transparent. And after the Big Bang, clouds of hydrogen and helium started to clump together because of the force of gravity. They started to form stars and galaxies and planets, and that's what we're observing at this time. So here's the basic idea here. So here's where the Big Bang happened. And you see then we have this part where it gets expanded. Now it was stable for a long time and now it's starting to expand again. So here's some telescopes. What they're really looking at, they're looking at over here. So when you're observing stuff, you're observing stuff that already happened. If you're looking at light, for example, you observed it, but it's the event that happened how many light years ago? So look at this timeline over here, 12 billion light years. That's crazy. So we can also date these things because of what's called the red shift. So as space has expanded, light traveling through it has been stretched as well, shifting its wavelength from the blue end of the electromagnetic spectrum to the red. And the further away something is from Earth, the redder it appears. And you have probably observed the same effect with sound. So say you're sticking your head out the car window and you're looking at a car coming from the other direction. The sound, you can tell it gets closer and closer. Then as it passes by, it has a different sound, right? So as the sound wave is coming towards you, you're getting more sound waves hitting your ears per second. And as it passes you, then you're getting less and less sound waves hitting your ear per second. So it's the same phenomena. That's with sound waves. This is with light waves. So stars are made from clouds of gas that are compressed with gravity to the point where nuclear fission starts to begin. Fusion, I should say. And so I tried to summarize it by drawing this. And believe me, I'm not an astronomer. I know astronomers. So here's hydrogen clouds. They get forced by gravity into becoming hydrogen stars. Now, our sun is a hydrogen star. What will happen to our sun? As fusion starts to wane out, it's going to turn into what's called a red giant and end up as a white dwarf. And while we're at it, what if the cloud is too small for it to become a hydrogen star? Then it becomes a brown dwarf. So right now we've just described a whole bunch of things that we see out there with our telescopes. If the hydrogen cloud is big enough, that hydrogen star can then collapse into what's called a carbon star. If it's even bigger, it can collapse into an iron star. If it's even bigger, it may collapse into a black hole. So, remember we talked about iron being the most stable element in the universe, right? Well, what can happen here is that these iron stars, if they're big enough, the force of gravity is so great that electrons are simply smashed and pushed into the nucleus, combines with protons, and all you end up with is neutron stars. So many of these neutron stars are spinning, and they give off light as a pulsar. But sometimes what can happen is that these things explode. So as the star gets compressed, it compresses at a high rate, and it hits what's called that neutron core in the middle, where neutrons have already been formed from the large forces of gravity. So the neutrons are just extremely dense. So sometimes when the iron star collapses, it collapses or implodes, then it hits that core neutrons that are so dense that it then bounces apart. So that implosion becomes an explosion, and that can be seen as a supernova. So the supernova could send all these particles right back to being clouds of mass again, or it can actually implode more and become a black hole. And this is known as a quasar. And sometimes they believe that if the hydrogen clouds are so large, you can just simply bypass all that. There's a direct collapse right into a supermassive black hole. And sometimes they associate that with a super bright quasar. So I've tried to just give you a general idea about it. And does it have to do with chemistry? Yeah, it does. So the Earth and humans are essentially made of stardust from recycled stars. And Earth is constantly passing through extraterrestrial dust from asteroids and comets. And we have a way to measure that here on Earth by looking at iron 60. So iron 60 has been shown to be extremely rare on planet Earth. It doesn't come from processes on planet Earth. So when it does get detected on our planet, we know it came from extraterrestrial sources. So here's a couple of new pictures put together. So what are we looking at right here? Here's the black hole right here. Here's another sun or star or something like that. And the gases are being sucked off and pulled into this black hole. So some terminology that you may have heard of, the event horizon is right where once you get right here, there's no way you're going to be able to go away. You're just going to be ending up in here. And then for many years, they thought that nothing could escape from a black hole, not even light. However, Stephen Hawking, who was a really obviously a well-known astronomer, he predicted what was called Hawking's radiation coming out of black holes. And then they finally found that. And part of it is these jets that come out. So these jets were recently discovered. They're made up of electrons and nuclei and often heavy elements, that's iron and nickel, traveling super fast. So they're so powerful that the shock waves can cause the collapse of gas clouds into other new stars. Here's another one. And so here's another one. Here's two neutron stars colliding. So they observed this in 2017, two neutron stars colliding. It exploded into what's called a kilonova, the first ever observed. It's just huge. And anyway, they predict that the equivalent of 10 Earth masses of gold, silver, platinum, other metals were created during this collision. But all these pictures right here, what are we really looking at? Did somebody go up to Mauna Kea, take their iPhone and put it in front of the eyepiece and just took a picture of this? The answer is absolutely not. This is a computerized rendition coming from every measurable piece of data that we have. We're talking about, yes, visible light. This is interpreted in the form of visible light so we can see what it is. But it's infrared and gamma rays and neutrons and just everything, all put together into a computer image to see what we cannot see. So recently, this year in fact, it was published, Waves in the Galaxy, our own galaxy. So they discovered a titanic wave of gases spiraling through our own galaxy, the Milky Way. It contains thousands and thousands of baby stars and maybe even more. Never seen it before. The mass of these stars, growing stars in here, is way more than the sun itself. And by the way, it's now predicted that every galaxy in the universe may have its own black hole. It seems like we might be having a spiral over here somewhere to help us locate that black hole. So here was the first image of a black hole. Two telescopes on Mauna Kea were used to get this first image. By the way, speaking about Mauna Kea, why is Mauna Kea so important to astronomy? Anybody know?
Is it the altitude and the weather?
That's right, in the pristineness of the atmosphere. And at Mauna Kea, it's high enough that we can actually image with infrared. If you go to the Canary Islands, the weather is not very good. You would greatly reduce the number of useful days, and you would not be able to get any data from infrared. So even at Mauna Kea, they have to do certain precautions to block out the light coming from towns, coming from street lamps and all this other stuff. And I don't know, I remember when I was a kid, coming back and forth from the Big Island to Oahu, it was like you'd be flying into Oahu and it's like, oh yeah, there's the airport. Oh, those little lights over there, that must be Pearl City. And there wasn't much of anything back then. Now the times I've come back from the mainland, coming into Honolulu Airport, you can see Honolulu from just hundreds of miles away because of all the lights that come from it. So the astronomers, even way up there in Mauna Kea, have to figure out ways to reduce the interference that comes from the lights from Honolulu. So anyway, I just put some cartoons in here. Yeah, never trust an atom, they make up everything. And here's how I often feel after this lecture. And then I just love Dilbert. So he decided to build a particle accelerator in his basement. Sounds expensive, not if you use cardboard. My plan is to say I discovered one new particle every week. And when the scientists confirm my discoveries, I will just say they need better accelerators. See, his tail is wagging because, hey, you can't prove me wrong. Yeah. Yes, there's nothing wrong with stupid humor, okay? Okay, so review. I can go back to chapter 1 and start from there. Does that make sense? So introduction. And then what I want you to do is just ask any question. But if we have the chapter up, we can keep it within the context of what we're looking at. So hopefully you have mastered your calculators. Your calculators now listen to you. Scientific notation and all that kind of stuff. You should really know what a direct proportion is by now and our method of solving problems. Here's the 14, or here's 10 of them within the metric system. So really what you need to do is simply memorize what the symbol stands for. Right, I could have a picometer, I could have a picosecond, I could have a picadollar. And then you should know one way to get between United States and the rest of the world with mass. Let's see. Oh yeah, mass, length, and volume. Let's see. So temperature scales, you do not need to memorize the equations for this. I will give them to you. Let's see, then a whole bunch of practice there. And then here I'm trying to get you to think out of the box. So $10 per hour is definitely in the box, right? Matter of fact, my 7-year-old grandson has got this wired. And if you're not used to the metric system, that could be confusing for you, but it's the same math. Then I know you're not comfortable with this stuff. So why am I doing this crazy stuff? Because I want you to understand the math. It's the concept. It's not one particular application of the concept. And I still want one of those. Actually, that reminds me of yesterday. So we're down at the beach with my family, and Keone and his wife have a brand new Frenchie puppy. The thing is just so tiny. They brought it to the beach for a little while. And here's Keone, who's this big guy with all this tattooed arms and big old tattooed arms, and he's holding this little tiny Frenchie in his hand. I'm like, yeah, that's the cutest thing in your family for sure. So questions about any of the homeworks here? This is basically homeworks 1 through 3, right? This is homework 3. Percent. Yeah. So chapter 1 was pretty much remedial. Oops.
Professor, I had a question about, one more question about homework 3.
Yeah.
On question 4, it says convert 60 kilograms into meters cubed.
Right.
Use figs and units. And the first set of instructions are to use the graph, not the equation.
Right.
I interpreted this as you take the point along the y-axis, and then
Right.
you find out where that point along the line is, and then
Right.
you find out what the point along the x-axis is, which would be meters. The x-axis is meters.
Well, it's really the intercept. So if you look at y equals mx plus b,
Yes.
trying to find b, right?
Yes.
So mathematically, if you set x equal to 0, and mx is 0, it's gone now. So then y is equal to b. So if you just go to the x-axis and find where x equals to 0, you just read the y right there. And that's it.
Okay. Thank you.
So that's not calculated. That's just reading off of the graph. Make sense?
Yes. Thank you.
Okay. So after chapter 1 came chapter 2. That's why we use numbers. Okay, so one of the things that you need to do is know what significant figures are. That anything that's measured and written down is a significant figure. An uncertainty is what occurs or is assumed to occur in that last reported significant figure, right? So here's 5 significant figures. The uncertainty would occur right there in the hundredths place, right? And what that means is that this person wrote down the number to the best of their capabilities is 200.00. Somebody else might do the same and come up with 199.99. Someone else might come up with 200.01. So that uncertainty allows for uncertainty. And so you can see that the uncertainty increases by a factor of 10 whenever you have, smaller numbers, right? And so the importance of that decimal place right there, distinguish between 200 with 3 significant figures and 200 with only 1 significant figures, is pretty important. And so I think I gave a pretty good idea of what is accuracy and what is precision. Precision is just how close your data points are, but that has almost nothing to do with accuracy. And most of the time, when we are trying to measure something that we've never measured before, all we have to go by is the precision. And we hope that good precision means good accuracy. Doesn't necessarily mean that. So here are some examples on how to measure things in real life. Hopefully that helps. And then we get to calculations. So in effect, if you're doing a laboratory experiment, everything that you measure is going to affect your final number. The more things that you have to measure, the more uncertainty, and all that uncertainty builds up and has to be expressed in the final answer. We're not going to go through that extreme, but we're going to just be able to do it in simple, one-step calculations. So in multiplication and division, you go by the least number of significant figures. People don't have a problem with that, but they do have a problem oftentimes with addition and subtraction. So here, we're ignoring significant figures and we're going by uncertainty. So again, I'm looking at these 3 numbers right here. The biggest uncertainty is in the tens place, which is where I have to round off, right? Here's my final answer. What we're really doing there is this. You're lining up the decimal points, doing the math, get the unrounded answer, and then I can keep anything that's in common with all of the numbers. So here, I cannot keep in the hundredths place, but I can keep in the tens place. So I'm throwing away a 0.09, so I have to round the next one up. Okay. So there's a bunch of examples of that. And oftentimes you get numbers where the decimal places are not lined up because the powers of 10 are different. So you can put these numbers in your calculator and you will get the right answer. But then in order to round off, you have to really line up the decimal place, which means make the units the same, make the powers of 10 the same, and then you line up the decimal places. And then you can figure out where to round off. Okay. So then I put a bunch of discussion points in there, and it's not going to be specifically on the test, but it may come up in part of a true false question or something. I don't know. So anybody have any questions about the nuts and bolts of rounding off and doing math with significant figures?
How about when there's like multiple steps like in the calculation? Because an example in homework 4, when you were converting the Fahrenheit into Kelvin, I wasn't really sure like if I was supposed to round off after calculating Celsius and then move on to Kelvin, or
Well, no, you never round off in the middle of a calculation. Never.
okay.
So say, for example, you do a first calculation, you get 1.333333, and the threes just keep going on forever.
Mm-hmm.
If you were to round off to 1.3 right there, that number is different. 1.3 is different than 1.33333, right?
Yeah.
So you would keep that whole number on your calculator, or at least enter it with a whole bunch of those significant figures, so it won't affect your next calculation.
Okay.
Make sense?
Yes. Thank you.
So in that particular problem, I know some people were confused with the 1.8. The 1.8 does not represent two significant figures. It represents an infinite number of significant figures because that was a definition.
Okay.
It was never measured. Like 12 inches equals 1 foot. It's a definition. It wasn't measured, right?
Yeah.
So it's an infinitely precise number.
Thank you.
Okay.
Professor, on page 5 of chapter 2, there's a series of examples written. And for example, on the third bullet point, it says the answer is -1 degree Celsius.
Uh-huh.
Why isn't why isn't it indicated where the uncertainty is in the answer for that example?
Oh, it is right there.
Okay.
Yeah. Okay.
Okay, thank you.
So it just turns out that the uncertainty for both numbers were the same. So it ended up as this uncertainty was the same, right? So when I write this number, it really means that same thing, right?
Okay, so that's just a clarification on that, I guess, where your cursor is right now.
Yeah.
Okay, thank you.
So now that you know about this, if you're looking at this number right here, and you don't know where it came from, but you're simply looking at this number, you would be able to say that, oh, the uncertainty is right there, right?
Yes.
That number has 3 significant figures.
Yes.
Mm-hmm. Okay. So any questions about the other stuff here? Vitamins. Why did I write all this stuff? Am I crazy? Am I really trying to make you think like a scientist, one who questions everything? Okay, should I go on to the next chapter?
Yes, please.
Okay. Where is this thing? And it takes a lot of clicking to get screen sharing to going. Okay, so there's kind of a lot of, I guess, definitions and concepts in this chapter. So the basic one is that heterogeneous and homogeneous. If it's homogeneous, it can either be a pure substance or a solution. And the major difference is that a solution being made up of a mixture of substances, the properties will change according to how you make up that solution. Like you can make a solution full of sugar and water, and it could be just so little bit of sugar in there you wouldn't even notice it, or it could be so sweet that all the kind of properties are just changed. It just basically turns into a syrup. In a pure substance, the properties will always be the same. It can either be an element or a compound. So elements is only one type of atom. It could be a simple atom, or it could be a molecule, which is more than one atom held together in a bond, for example, oxygen molecules. If it's a compound, then it's made up of more than one different kind of element. Okay? So H2O is not an element, but it's a compound. Okay? And later on, we'll see that these are held together by covalent bonds, sodium chloride by ionic bonds. And then to decide whether something is a compound or an element, we basically just take it and we try to break it down into other substances. If we can't, then maybe it's an element. And what is the periodic table of? It's the periodic table of the elements. All the elements that have been discovered. The next chapter, which we'll do tomorrow, is on the periodic table. So, yeah.
I have a question, Professor, about, if you could scroll up a little bit, about what is the difference between a molecule and a compound?
Okay, well, they both have bonds, right? But if it's a molecule, this has bonds. But if the bonds are between two elements of the same element, then it's still an element. But if they're different elements, then we call it a compound.
Oh. So you can have a molecule of like one element, and it's not, is it still called a molecule though?
Yeah.
Okay.
Like H2, O2, Cl2, all those things, they're elements, although they're molecules, because one element is bonded to another element.
Okay.
So if there's bonds in it, then it's a molecule.
Okay. So it could either be like a pure molecule or like a molecule with that's like mixed up.
Well, it could be a pure element, like O2 is a pure element. And you could have pure water, and that's still a molecule, but it's not an element anymore. It's made up of elements, so it's called a compound.
Gotcha.
So here's a compound. Your ethanol is a compound, right? Not an element. These
Because
are
it
bonds.
has two different more than one kind of element in it.
Exactly.
Right?
Exactly.
But if it has the same element, maybe if it's like H2, then that's a molecule, but not a compound.
It's a molecule and an element. Yes.
Okay.
So it's either going to be an individual atom, or it's going to be a molecule. If there's bonds, it's a molecule. But within that, if all the elements are the same, all the atoms are the same element, then it's an element. And if they're different, like in H2O or ethanol, then it's a compound. Okay, and then the law of definite proportions is basically saying that H2O is always H2O. It's not H3O, it's not H2O2, right? And this was a major step in understanding chemistry. And it didn't come until 1800. But even at that time, they didn't know what an atom was. So they had to go by describing something as, you know, what was it? So they would have to break things down into, you know, percent hydrogen, percent oxygen, that kind of stuff. And that's what they had to describe stuff. They couldn't say it was H2O like we do now. It was all by, oh, it's 11.2% hydrogen and the rest of it is oxygen. So that last part of chapter 1 where I went into percentages was really important so you could figure out how to do this stuff. So I'm not saying this stuff is easy. I'm just saying it takes some thought. So let's look at the last problem here. Given that carbon dioxide is 27% carbon, what does this mean? That 27% carbon is a conversion factor. That means that 27.29 grams of carbon are there for every 100 grams of carbon dioxide. Okay. So how many grams of carbon are required to make 250 grams of carbon dioxide? That's 250 grams of carbon dioxide. See how I thought through that? And then I'm using the units. I have to cancel out grams of carbon dioxide and keep grams of carbon. So to do this problem, you first recognize that the percent carbon is a conversion factor and that everything is a direct proportion and that you're going to use the units to set this problem up. So then that was compounded by the law of multiple proportions, which, you know, just made it that much harder to really understand. So then density, I did not treat density like something that you memorize an equation, then you just plug into the equation. I treated density like the other conversions because density is a direct proportion. And I proved that to you right here, right? So we're doing y is equal to mx and b happens to be 0 because it's a straight line passing through the origin. So if I want to turn milliliters into grams, I have to use that line, which is representative of y equals mx. So now we're looking at a problem like this. How many grams of gold and so many milliliters of gold if the density is this? I look at the density as being a conversion factor. It converts me between grams and milliliters. Okay. So please stop me if you have any questions. So it's density that really tells us where we're supposed to be in the universe. It's the law of gravity, force of gravity that enforces that. And isn't that true also anywhere else in the universe? why is a star where that star is? What is a black hole doing? It's basically doing the same thing that the center of our Earth is doing, pulling things towards it. It's one of the four forces of the universe. Doesn't mean we understand it, but we know it exists and how it works. Then I'm talking about the density of water versus temperature. And that was a lead into specific gravity. So specific gravity, what you're really doing is you're comparing the density of a sample to the density of water at that temperature. So the temperature is different. So here's an example where the specific heat of seawater is given. So here's the density of seawater compared to the density of water at about 4 degrees, right? And notice that grams per cubic centimeters cancels out. So specific gravity has no units. And of course, that becomes an issue now when you're being told to use units to solve all the problems. So similar to density, I don't think you have to memorize an equation and then not know what the equation means. What I would like you to understand is what is the understanding of density and what is the understanding of specific gravity. What does it mean? It's the density of some sample compared to the density of water. So hopefully you won't have to memorize that equation. So here we're given the specific gravity of a urine sample and then asked what is the density? The density of water is given. So looking at this as an equation, I have given this and I'm given this, I'm simply going to solve for this. So algebraically, this is what I get, and then I just substitute into it. And notice that even though this had no units, it ends up with units when you do the multiplication. And so you see why I rounded off to 4 significant figures, yeah? This has 5, this has only 4, so my answer can have only 4.
I have a question.
Yeah.
Let's say we were to have this question on the exam. Would we have this equation, the SP specific gravity equation for us?
Not necessarily. Just like with density, I wouldn't like, here's the density equation. You should just know what density is. And you should know what specific gravity is. I know many of you may feel more comfortable if you just had like a list of equations or memorize them. But then my issue with that is that you're giving up on trying to understand. Okay? You're telling yourself, well, this is science, I can't understand that, so I just have to memorize something. That's my feeling. So then, why do we use specific gravity? 2 reasons. One, it's one measurement. It's very easy to measure with an adequate number of significant figures. So here are several ways that we can do that. The other reason is that in general, the changes in specific gravity with temperature are kind of minimal compared to the changes in density with temperature. Like here we have a solution. So we're assuming that solution is made out of water. Wait, that's not a good one. yeah, here's the solution. And we're assuming that it's made out of water. And so look at this. If I increase the temperature, the density of water will decrease, but so will the density of that solution decrease. Not in the same amount, but they're going in the same direction. So the net result on specific gravity is not going to be as great. So mass and weight, hopefully you know the difference, at least, conversationally. Okay. Weight is actually a force, and it's not a mass. Okay. If I want to convert weight into mass, then I need a conversion factor, right? It converts weight into mass. That conversion factor depends upon where you are in the universe. The mass does not depend upon where you are in the universe. So then, to truly understand chemical reactions, we need to know the law of conservation of mass, which is the reason why we balance chemical reactions. So we're not required right now to learn how to balance reactions. We'll do that in another chapter. But that's the reason why we do it, because the mass on this side has to equal the mass on this side. Over here, that doesn't occur, right? Because it's not balanced. And the law of conservation of energy also is obeyed by chemical reactions. So the total amount of energy here is equal to the total amount of energy here. That's why we use that heat. So that can be put into an energy diagram. Okay. It helps kind of explain that. Okay. By the way, you can look at an energy diagram as like, say this is a cliff and we have a ball or a rock up here on this cliff. When I push the rock over this barrier right here, this energy barrier, this is energy, right? It's going to fall down here. The energy that I need to push it up here is regained when it comes down here. But now, between here and here, tells me that that reaction is going to happen. That rock is going to roll down the hill. And when it does, it's going to give off all kind of energy. So we can apply some observations to decide whether a chemical reaction has happened or not happened. And then the only purpose of putting nuclear reactions right here is so that you realize what a nuclear reaction is. It is not a chemical reaction. Chemical reactions have only to do with electrons, nothing else. You can gain an electron, share an electron, you can lose an electron. That's all you can do with an electron. If it's not an electron, then it's a nuclear reaction. So here's an example where you have 92 protons in a nucleus, and now you don't. So the element changes from uranium into thorium in this case. This is a nuclear reaction. Just some definitions. Energy is basically this definition because I'm not going to ask you an equation about force times distance. It's just furthering your understanding. But you should have a good idea what is heat and what is work, different kinds of energy. So this example right here, Rumford's machine. He took mechanical energy, right? Converted it through this machine right here and produced heat energy. Same thing with Joule's machine. He took mechanical energy and converted that into heat energy. When he set this up, he used potential energy that converted it into kinetic energy, which manifested as heat in this part of the machine. Then this is kinetic theory. Kinetic theory is almost always taught in the chapter on gases. I'm teaching it to you now because I want you to see that this is universal. It's not just about gases. So the temperature is proportional to the kinetic energy. I can use the equal sign here if I decided which temperature scale to use. If I increase the temperature, I increase the kinetic energy, and that really translates as an increase in velocity of the particles. So if I were to take a piece of metal and I heat it up, and it's still a piece of solid metal, the velocity of those individual atoms has increased. They're bouncing around in the same place, but they're still vibrating at a higher velocity. If I increase the temperature even more, those vibrations become so violent, so large, that I might be able to break the attractive forces holding those atoms together as a solid and cause the solid to melt into a liquid. If I increase the temperature even more, those individual metal atoms are going in such large velocity that they can break away from the attractive forces that hold them together as a liquid. And they can now go into the gaseous form. So the law of conservation of energy states that in a system in which this is not necessarily a chemical reaction, but even if it was just a chemical reaction, in that system, the total amount of energy stays the same. You may interconvert between potential and kinetic energy, but the total energy is the same. Here we applied that to chemical reaction. So here's ATP, which you guys are burning right now. So ATP and water have a lot more potential energy than on the other side. So the total of potential and kinetic energy over here, though, has to be equal to the total of potential and kinetic energy over here. So the amount of potential energy in ADP is much lower than it is in ATP, but that energy that's given off as kinetic energy is significant. And this is the amount of energy that can be used to do work.
Excuse me, Professor.
Yes.
So the potential energy, because I have here written in my notes that the potential energy has to be, I guess, balanced in these equations. And my understanding is that the potential energy in ATP is more than the potential energy of ADP. However, I guess the remaining potential energy is converted into that kcal, the 7.3 kcal. Is that correct?
Here's a good reason to have an energy diagram there. Let's go back to the energy diagram. So here's ATP and water.
Yes.
Here's ADP and phosphate and that energy.
Yes.
There's more potential energy in the reactants than there is in the products. So where did that go? That was given off as 7.3 kilocalories per mole of ATP.
Okay.
Right?
Yes.
So But this still has some potential energy. It's not zero.
Right.
Yeah?
But it's not as much as it was when it was at the top of the graph
Right,
because of the release through kinetic energy. And yeah,
right.
okay.
Okay, then we have specific heat. So specific heat or heat capacity is energy required to change the temperature of something. So what if it's hard to change the temperature of some substance? That means that you have to keep putting energy and energy and energy into it, and it absorbs that energy, but it doesn't change the temperature very much. So that's like a heat sink. Then you take something like a metal where the specific heat is a low number. That means that you put energy into it and the temperature changes very rapidly because it's not really holding on to the temperature, it's just using it to change the temperature. So essentially, high specific heat molecules are heat sinks. Low specific heats like metals are not. Instead, they transfer the heat from one object to another. So think about if you're boiling some water in a pot, right? So you boil some water in a pot and then you take it off and that thing takes forever to cool down. The reason is that the water absorbs so much heat energy, it just simply takes a long time for it to cool down and get rid of it. But if you pour the water out of the pan, that pan cools down pretty quickly, doesn't it? It doesn't hold on to the heat, it simply transfers it. Whereas the water holds on to the heat. So here I tried to show you where the definition of specific heat came from. It really came from the definition of a calorie. Because if I use water, I end up getting the specific heat of water. It's just simply this grouping of units, right? So yes, again, specific heat is a direct proportion, even though it has 3 units. And I'm treating it just like how we did, converting between centimeters and meters and density and specific gravity. Specific heat will use it as a direct proportion, and simply the units will then guide us how to solve that problems using the specific heat. It may be confusing that I even put this in here, but I kind of have to just explain to you why your textbook is different than the others. But look at this information here. It's the same as the units tell you. Why do we need to memorize all this other junk? It's ridiculous. So let's look at the problems here. So how many calories are removed to cool from 100 grams of gold from 50 to 45, given the specific heat? So I have to realize that the specific heat, like the density, is the conversion factor. But we're confused because there's 3 units in there instead of just 2. But using the units, they're asking for calories. So I wrote it like this, so calories will be on the top and calories will be in my answer. Now this quantity is equal to 1, right? So I'm allowed to take 1 and multiply by other numbers. So what do I need to do with grams? I need to get rid of it. So I multiply by grams, cancel out grams on the bottom. Similar with temperature change, get rid of temperature. So I get only units of calories left over. So why does this method work so well? Because here, I'm asked for mass, right? So I don't want mass to be on the bottom. I want mass to be on the top. So I simply took this quantity equal to 1 and flipped it over to suit my needs. So I want to have grams left over at the end. So I have to multiply to get rid of calories. I have to divide to get rid of the temperature change. And my units are simply grams. So here they give you a bunch of data. Well, what is the specific heat? The specific heat is defined as this grouping of units. It's the energy divided by the mass divided by the temperature change. So I just do what the units tell me. Take this, divide by this, divide by that, there's the answer. Would I do anything different if instead of calories, I use joules? Be the same calculation, wouldn't it? What if I use Fahrenheit instead of Celsius? I'd be doing the same thing. So, questions so far about specific heat, maybe? So then we looked at calorimetry. So we used the specific heat of water generally to do calorimetry. So we used the specific heat of water to get these conversion factors for food. How many calories is in a gram of fat or carbohydrate or protein? Now we can use that to figure out how those calculations on your food labels are done. Okay. So you simply take the grams of fat that was analyzed in that particular food, then convert that grams into calories for each of the 3 components that actually give us significant calories. And then we add them up. Okay. So in terms of significant figures, I showed you how I was able to figure out how to round off. I don't think it's that important. The most important thing is for you to get this calculation, okay? And I just told you one of the things that I look at, and I think it's probably one of the most important things, is how much calories in that particular food come from fat. I think it's an excellent way to compare calories, commonly done in nutritional circles. And yeah. So in this particular case, you have 306 calories that came out of the total sample, which was 591. So that's how you get the percent fat calories. And the rest of it is other simple direct proportions, converting calories into time using these energy expenditures, okay? And of course, all of these things use kilocalories, right? Nutritional calories and metabolic calories are all kilocalories. I think this stuff is pretty simple. So does anybody have any questions about the nuts and bolts of doing these problems? Okay, how about discussion points? So not necessarily on the exam, but I'm just trying to make you think.
I had a question on page 24, number 8.
24. Oh yeah, the big fat review. Yeah.
About the melting point. I was kind of lost on this number. I was hoping perhaps you could explain it once more.
Mhm. The number?
Number 8. Yeah, I just couldn't really follow why. I mean, for example, why the heat energy would flow to the butter, and
Oh, okay. Well, heat energy goes from the hot object to the cold object. And this is what we use temperature for, right? So if you're 37 degrees and the butter is going to melt at 35 degrees, you're going to transfer heat energy from your body to the butter. You're going to melt the butter.
I see.
It's going to melt in your mouth. It's another way to think about it. Okay?
Uh-huh.
So that's what I mean by which direction would the heat energy flow. It's going to go to the colder object. Okay? And then after that butter and you became one, you're both going to be 37 degrees.
Wouldn't I lose heat energy if I transfer it to the butter though?
Yeah, but you're thermoregulated, so you're going to use energy from food and everything to maintain your body temperature at 37 degrees, where the butter is not going to be able to do that.
I see. Okay, thank you very much.
Sure. Okay. Anything else on that chapter?
I had a question going back to page 1 on just understanding on elements, atoms, and molecules.
Uh-huh.
And I'm wondering if you could just go over again that oxygen can be an atom and also an element, but then when there's two, it's a molecule.
Right. So, what's a good way to show that? I'm going to see if this works. I'm going to hold it up to the camera. Because I know I'm a visual learner. You see that? Does that show up or is that reversed? I can't tell.
Yeah, we can see it.
Okay. So oxygen by itself is simply an atom. But oxygen molecules, the ones that go up our nose, are O2. They're held together by a bond, right? But both of them are made up only of oxygen atoms, so they're both elements. So oxygen can be an element as an atom and also as a molecule. But if I take water, water is a compound. This is a compound and it's not an element. It's still a molecule, right? So if you see something with a bond in it, it's a molecule. But it could be a compound or it could be an element. Does that make sense?
Yeah, thank you. So the molecule is the umbrella, and then if it's a molecule, it could then be an element or then be a compound. Is that right?
Yeah, sure.
Thank you.
Yeah. Okay, should I go to chapter 4? Okay, so atomic theory. So, atomic theory was very, very early in 1808. But it was so important because it started to make everybody realize that understanding matter and energy can be done. It's a system. We just got to figure out the system. Then what we need to understand is the three-particle model of the atom. And I'm not going to ask you specifically, oh, how were electrons discovered? What year were they discovered? No, I'm always asking you questions about understanding, and not historical and not like minuscule, but really, can you do problems and understand what you're doing? So protons and neutrons and electrons are the three-particle model. The nuclear model, how it was discovered, was important because it's so typical of science. You might set out to prove something, but you ended up unproving it, and vice versa. So theories are important to try to help you decide how to do an experiment. But really, everything has to be validated by an experiment. And even when you get the experiment done, other people may interpret it different ways. So that just causes more experiments to be required. And that's the way science is. And the forces that hold together nuclear structure is basically why I had to go and do all the stuff at the end of this chapter about what are the four forces of the universe, just to give you some context. Otherwise, it doesn't make any sense. Otherwise, it's just like, oh, believe me, there's a force that holds the protons together in the nucleus. Like, well, I don't want you to take my word for it. I want you to see the discussion and the study of it. So then isotopes are something that we need to know about. And this is really about using the three-particle model of the atom, isn't it? Okay. So here's the three-particle model of the atom. So we need to be able to take this symbolism and realize, and be able to figure out the number of protons, number of neutrons, and number of electrons. And then relative mass. So I think I explained fairly well why we use relative mass. It's because when we take relative mass, it's not going to change, right? Because we're comparing everything to carbon-12, and we know carbon-12 is exactly 12 AMU because we defined it that way. This is exactly, there's 12 inches in a foot, right? That's a definition. But when we go to take AMU and convert it into real mass, which is grams, well, that requires measurement. And that might change. So in this part of the chapter, there's two conversion factors that I just wanted you to be able to be familiar with. You don't have to memorize them, but you should know how to use conversions with them. That is the AMU, the number of grams, and the moles, the number of things, okay, whatever they might be. So I might give you some rather simple question getting you to use these two conversion factors. And it's very esoteric, but the reason why you can do it is because you know it's a direct proportion, and these problems are solved by looking at the units. So now I'm trying to show you where the numbers come from on the periodic table. Okay. So those are not representative of any particular isotope. They're the average of all the isotopes on the planet in relation to how important they are, how much of each of them there are. So it's a weighted average. So the last calculation essentially is doing that, right? So where does the data come from? It comes from the mass spectrometer, and I think I explained that decently. So this is what the x-axis gives us. This is what the y-axis gives us. So the last calculation for this unit is being able to get this number down here. So given this data from the mass spectrometer, you multiply and then you add. And that's how we get those numbers on the periodic table. So here's a whole bunch of different calculations. Some of the ways that the mass spectrometer data and this stuff can be used. And then I went into all this esoteric stuff over here about four forces in the universe and the standard model of physics. And I'll be honest with you, my colleagues are like, what? You go through the standard model of physics? Those are my chemistry colleagues. But when I talk to my physics colleagues, thank goodness you do that. Because now you're making, you know, the how do you say, the relationship between chemistry and physics, which I think gets lost. So anyway, we're kind of out of time, so I don't really have time right today to go through and finish this review on this, but my plan would be for tomorrow, I'm going to start chapter 5, which is in unit 2. And if you have any questions more about anything in unit 1, please ask, you know, at the beginning of tomorrow's lecture. And then the other question I have for you, while we still have enough people here, for the Biochem 241, we could do two things with exam 1. I can make it available on Tuesday and Wednesday. Tuesday's tomorrow, by the way. Or I could make it available on Wednesday and Thursday. The problem with Wednesday and Thursday is that Thursday is Kamehameha Day. But Kamehameha Day does not shut down the internet, does not shut down Laulima. Besides, you guys are really not supposed to be socializing for Kamehameha Day. I don't know, maybe everything is kind of loosened up now, but what I would like to do is make the exam available to the 241 students on Wednesday and Thursday, despite Thursday being Kamehameha Day. What do you guys think about that?
Yeah, I think that would work.
Okay. And traditionally, when this is a face-to-face class taught in a 6-week summer session, you don't have much choice. It's like, hey, we got to get these exams done. There's 5 exams in only 6 weeks. I'm not hearing any objections. And then the other point I'd like to make about the exams is that exam 4 and 5, the way I usually do it in a short time period like this is I say, well, okay, 2 different days to take the exams. You can do exams 4 in one day, exam 5 on another day, or you can do exam 4 and 5 on the same day. Exam 5, which is the final exam, is not a 2-hour exam. It's not any bigger or different than the other exams. See my point? So just to let you know about towards the end of the class, don't be worried if it looks like we're running out of time, we're not. Final exams are normally 2 hours. And if you take exam 4 and 5 together, that's 2 hours exam. Okay. So any questions?
What are the questions like on the exam gonna be like? Is it gonna be like similar to the homework where it kind of goes through the problem step by step, or is it just gonna give you the question and then you just type in or select the correct answer?
Okay, so the type of questions will be like what you have on the homework, right? But when it comes to having to make the exam in, how to say, in this format, like say you have a 2-step conversion, I'll probably ask you, what is the answer to the first step? And it will be, you have a menu to choose from, right? And then what is the answer to the second step? So it won't be as detailed as putting in all the answers like on the homework or maybe even the quizzes. That makes sense to you?
Yes, thank you.
Okay. Any more questions? Okay, well, I will end it here. Yeah,
For Chem 100, we still haven't decided on when the exam will be, yes?
right, we haven't. We have a
Okay.
little bit more time because we
Okay,
have
great.
12 weeks. Yeah.
Excellent, thank you.
Okay, I'll get this up on YouTube pretty soon. Okay, you take care now. Bye.
Thank you.
Thank you.
Thank you.
Bye-bye.